So we will, to solve this question, we will first see and take out all the data that is given to us. So it is given that at Z is equals to L, that is at the top, our air concentration has 10% water in it. So XA1 is equals to, we will calculate this. First we will write XA2 is equals to 0.1. And how we will calculate XA1? We know that the concentration is partial pressure, vapor pressure upon total pressure. So our pressure in the question is given as 341 mmHg and our total pressure is 760 mmHg. So on calculating, we will get our value as 0.4486. 0.4486. So we also know that xb1 would be 1 minus xa1 and xb2 would be 1 minus xa2. So this comes out to be 1 minus, answer is 0.551 and this will be 0.9. So now let's moving on. What formula we will use in this question? What we have studied previously, that NAZ is C into DAB upon Z2 minus Z1 into ln 1 minus XA2 upon 1 minus XA1. This can also be written as NAZ is equals to C DAB. Z2 minus Z1 can be written as L and ln XB2 upon XB1. So we will now solve the values. For solving our equation, we first need to get the value of C. We know that C is P by RT and pressure is 760 upon 0.082 into 352 because the temperature given to us is 352 Kelvin. To solve this equation, we would first need the value of C. We know that C is P by RT. So in the question it is given that P is 1 atm. So we will take here as 1 and R is 0.082 liter per mole atm. So on solving it, we will get our value as 3.462 into 10 to the power minus 5 gram moles per centimeter cube. Now to solve this equation, we have the value of C and now we also need DAB. Since we know that in air almost 78 to 80% is N2, so we will consider DAB as 0.36 centimeter square per second. So on putting the value, we will get our NAZ is equals to, so we have put the values in the calculator and we will get our answer, which is equals to 5.459 into 10 to the power minus 7 gram moles per centimeter square second. So we got our NAZ as this and hence solved our question. Now let's move on to the second part of the
We
video.
just learned diffusion of A through non-diffusing B. Now we will move on to diffusion in a 3-component gas system. So consider a liquid water which is species 1 is evaporating into air regarded as a binary mixture of N2 and O2 which is species 2 and 3 respectively. Take air-water interface to be at Z is equal to 0 and top end of the diffusion tube to be at Z is equal to L. Flow rate of air flowing over container maintained such a way that concentration at top remains constant at X1L, X2L and X3L of water, nitrogen and oxygen respectively. If diffusion tube has a length L and at given temperature and pressure, diffusivity of water in N2 is D12, diffusivity of water in O2 is D13. Derive the equation for concentration profile for water and concentration profile for nitrogen and oxygen when water flux is given. Neglect solubility of N2 and O2 in water. So, just like the previous question, but with a slight difference, that here in last question we considered air as one entity which is B and water as one entity as A. But in this question we are considering A as a binary mixture of N2 and O2 and water as species 1, single species. So given in question that this interface of air and water is maintained at Z is equal to 0 and the top air is flowing at Z is equal to L. So let us say this is Z1 and this is Z2. This is species 1, N2 is 2 and O2 is 3. So here we will have, since it is a 3 component system, 1, 2 and 3, we will have 6 diffusivities. D12, when water is diffusing in nitrogen, that is D12. D13, when water is diffusing in oxygen. D23, when nitrogen is diffusing in oxygen. D21 is nitrogen diffusing in water. D31 is oxygen diffusing in water, and D32 is oxygen diffusing in nitrogen. So we have 6 diffusivities. But like said in question, that we have to consider the solubility of N2 and O2 negligible. So all these 3 will be cancelled. So what we are remained is with these 3. D12, 13 and 23. Now, since we know that we also take one more assumption that N2 and O2 are inert and won't react with each other. So we will consider D23 as negligible. So we have to consider only D12 and 13, which is N2 diffusing in water and O2 diffusing in water. In Fick's law, which is given as Ja is equal to minus D, is the equation we get for solving N1Z, which is molar flux of water in Z direction. Now we will write equations for N2Z and N3Z, which is nitrogen flux for nitrogen in Z direction. So the equation will be similar like N1Z, CD12, because water is diffusing in nitrogen, dx2 upon dz plus x2, which is the molar composition of nitrogen, N1Z plus N2Z plus N3Z. Similarly, for N3Z, equation will be like minus C D13 dx3 upon dz plus x3 into N1Z plus N2Z plus N3Z. Now we know N2 and N3 are 0. So this is 0 and this is 0. So this equation, which is our equation number 2, this equation which is 3, it will be like, and even your LHS, this is 0. So 0 is equal to minus C D12 dx2 upon dz plus x2 n1z, because both n2 and n3 are 0. So take it, rearranging it, we will get C D12 dx2 upon dz is equal to x2 n1z, which will reduce to dx2 upon dz is equal to n1z upon C D12 x2. Similarly, for n3z we can write dx3 upon dz is equal to n1z C d13 x3. Now integrating in both the equations, let us say this is your equation A and B. So we will integrate equation A dx2 upon x2 from x2L, from x2 to x2L. We'll give n1z upon C d12 and writing the limits of dz from 0 to L, from Z to L. On integrating it, we will get x ln x2 minus ln x2L is equal to n1z L minus Z upon CD12. Okay. Now we know property of logarithmic, ln A minus ln B is equal to ln A by B, and then removing log, so the final equation will be like x2 upon x2L. So integrating it, we know integration of 1 by x is ln x. So integrating dx2 upon x2 will be like ln x limits x to L upon x2, and your right hand side will be CD12. Limits are L and Z. So integration of dz will be Z, and taking the limits, it will be L minus Z. So here ln x2L minus ln x2 is equal to N1Z CD12 L minus Z. Now we can write this as x2L upon x2. This remains same. Removing log, so this will be like x2L, or we can write x2 upon x2L, taking the minus sign here, N1Z upon CD12 L minus Z. So this is how the equation reduces. Similarly, you can write for oxygen x3 upon x3L is equal to minus 1Z CD13 L minus Z. So this is what the equation reduces to. We also know that x1 plus x2 plus x3 is 1. It will be 1 at any point of time. These are the molar concentrations of water, nitrogen and oxygen. So the summation of all the molar concentration is going to be 1 at any point. This is like a logical boundary condition. So we can substitute that here. We know x3, we know x2. So we can write for x1 is equal to 1 minus, so what x2 will be like, x2 is going to be x2 is equal to x2L into this term minus N1Z. So we can substitute this here, so it will be like 1 minus x2 minus x3. So x1 is equal to 1 minus x2L exponent. Oh, here I forgot to write the exponent here also. So it will be like 1 minus x2L exponent minus. Solve a question. It is similar to the last question we solved. The question is, consider liquid water species 1 is evaporating into air regarded as binary mixture N2 and O2 at 1 atm and 352 Kelvin. Take the air-water interface to be at Z is equal to 0 and the top end of the diffusion tube to be at Z is equal to L. Vapor pressure of water is 341 mmHg. Air flowing over container contains 10%, 75% and 15% water, nitrogen and oxygen respectively. If the diffusion tube has a length of L is equal to 11.2 centimeter, at given temperature and pressure, diffusivity of water in N2 is 0.364 centimeter square per second. Diffusivity of water in O2 is 0.357 centimeter square per second. Find its value of mass flux for given case. Neglect solubility of N2 and O2 in water. So unlike previous problem where the diffusivity of N2 and O2 both were 0.36, here the diffusivity of nitrogen in water, which we designate as D12, is given as 0.364 centimeter square per second, and D13, which is of water in O2, it is given as 0.357 centimeter square per second. Again, the vapor pressure PV is given as 341 mmHg. So we can find the concentration of water, which is Y1 PV upon total pressure. 341 upon total pressure is 1 atm, which is 760 mm of Hg, which will be a 0.44889. So we designate this as x10. In the question, as we read, we are given x2L, which is the composition of nitrogen in air, 75%, which is 0.75. Oxygen composition is 15%, 0.15. And your L, length of the tube, is 11.2 centimeter. As derived in the formula, we will need concentration of water. Concentration of water is given as P upon RT. P is your 1 atm, R is your 0.082 liter per mole atm into temperature 352 Kelvin. which will be your 3.462 into 10 raised to minus 5 gram moles per centimeter cube. Okay, so we have all the variables that we require. Substituting them in the equation, we will get x10 is equal to 1 minus x to L. X to L is your 0.75 exponent minus n1z, which we have to find out, into L 11.2 upon C, your 3.462 into 10 raised to 5. All the units are in the CGS system, into minus x3L, which is your 0.15, into exponent minus n1z into 11.2 upon C, 4.62 into 10 raised to 5. Here a term d12 is also to be multiplied, I forgot, into d12, which is 0.364. Here also d13, which is your 0.357. So, and your x1 naught is 0.449. So, uh, substituting all the values we have done, finding n1z, we will get as 5.5. So your n1z is 5.505 into 10 raised to minus 7 gram moles per centimeter square. All the units are in CGS.
So we now want to examine a problem that is slightly different from the one that we have discussed previous to this problem. So instead of maintaining the liquid gas interface at constant height, we will allow the liquid level to subside as the evaporation proceeds. So basically what we are saying is that this is our tube and this was the liquid level initially. After, let's say as time is t is equals to 0, so after some time at time t is equals to greater than 0, the liquid level would change, and this is denoted by z0 and this one would be denoted by this. So the change, this is h of t and z2 is this. Z2 would remain constant, only z1 is changing. This is z10 denoting the initial value of z1 and this is z1t denoting the final value of z1, and this would be our value of capital H. So since the liquid retards very slowly, we can use a quasi-steady state method. So what is quasi-steady state method? Here basically what we are doing is we have already seen that our equation is NaCDAB Z2 minus Z1 ln XAB XB2 upon XB1. So this was a quasi-steady state for previous question. Now in this question we are replacing NaZ with rho Ma dz1 by dt, and we are multiplying both left hand side and right hand side by s. We also know that we can write xbln. This is our average value as xb2 minus xb1 upon ln xb2 upon xb1. So we will put this in this equation and we will get something like CDAB. This part remains constant. Instead of z1 it would be z1t, because now z1 is a function of time, and replacing this with xb ln xa1 minus xa2 into s. We have multiplied both sides by s, and where rho a is the density of pure liquid A and m is its molecular weight. So how we obtain this equation is basically, so this part is basically rho ma dz1 by dt. So we know that this is density is mass upon volume. So mass upon molar mass becomes moles upon volume, and dz by dt we know is velocity. So this basically is characteristic velocity into the property that is changing, which is our concentration. So here it becomes convective flux into area, which is our S. So we know that convective flux into area is rate. So we will obtain the rate of evaporation of water over the time period T. Now moving on, if we have assumed that we can denote small ht as Z10 minus Z1t, basically we are denoting this part h small ht by Z10 upon Z1t, and capital HT is Z2 minus Z1 naught. So taking the now we will do is what we will do is we will integrate the equation. CDAP would remain constant, Z2 minus Z1. We will bring this term this side and this term on that side. So it will reduce as follows. First we know that Z2 minus Z1t is our h plus h. From the equation, from the figure we can see that. And then moving on, we can write dz1 by dt is dh1 by dt. So dt gets cancelled. So this equation would reduce to first um, h plus h into dh is cdab, which is our this term, upon rho into ma. We have just brought this term rho into ma down here, and it becomes rho into ma into xbln. We are leaving this term here only, and then into xa1 minus xa2. These terms are written as it is, and s and s gets cancelled, so we are left with equation this. And we know that t is varying from 0 to t, and then h is varying from 0 to h. So on integrating and solving, we will get half capital C is CDAB xa1 minus xa2 upon rho into ma into xpln. And if we want to get the equation of h of t, we can write it as h of t is h root 1 plus c t by x square minus 1. So we will obtain this equation. So we have studied this concept, and now we will move on to a problem involving that concept. The question is something like the diffusivity of gas pair O2CCl4 is being determined by observing the steady state evaporation of carbon tetrachloride in a tube containing oxygen as shown in the figure, which is this figure. The distance between the CCl4 liquid level at the top of the tube is 17.1 centimeter. The total pressure of the system is 755 mmHg, and the temperature is 0 degrees Celsius. The vapor pressure of CCl4 is 33 mmHg, and the density of CCl4 is 1.59 gram per centimeter cube at that temperature, which is 0 degrees Celsius. The cross-sectional area of the diffusion tube is 0.8 centimeter square. It is found that 0.028 centimeter cube of CCl4 is evaporated in 10-hour period. After steady state has been attained, what is the diffusivity of gas pair O2 and CCl4? To solve this question, how we will begin is we will first note down what is the data that is given to us. So we know that here we obtain this equation. So for solving this question, we have studied this equation. Since it has become very trusted, I am going to rewrite the equation. It is minus S rho A upon ma dz1 by dt is CDAB z2 minus z1 as a function of time xa1 minus xa2 upon xpln logarithmic mean value. So here it is basically Na into S. To calculate the value of Na from here, we will write rho into S into dz. We all know that it is our volume. So it would be volume upon ma into dt, and time period is given. That time is 10 hours. Into S, because this whole term was Na into S. So to get Na, we need to divide it by S. So by placing the values 0.0208 centimeter cube into 1.59 gram per centimeter cube, Ma of CC, we have assumed our species A to be CCl4 and B is O2. So calculating the molar flux of CCl4. So we know that the mass of molar mass of CCl4 is 154 gram per gram mole. We are taking the CGS unit here, and our time would be, time is 10 hours, so 10 into 10, 1 hour is 60 minutes and into 60 seconds. So it would be 3600 seconds. 36,000 seconds. So into 0.82, which is the surface area, and into 36000. So on solving this value, we are getting it 7.26 into 10 to the power minus 9 gram mole per centimeter square second. Now of this equation, we have obtained the left hand side. To solve, to get the value of DAB, we need here. So we are going to put the value of what we have obtained and get the DAB from here. So DAB, on rewriting this equation, DAB is Na at Z is equals to Z1 into Z2 minus Z1, which basically moving Z2 minus Z1 here upon CLN XP2 upon XP1. We also know, to get the value of C, we know C is P by RT. So the equation will be like NAZ as Z is equals to Z1 into Z2 minus Z1 by into RT upon pressure into ln PB2 by PP1. We know that we can write it in terms of partial pressure. So on placing the values, it would be 7.26 into 10 to the power minus 9, which is the value that we obtained here. So our value of NAZ is 7.26 into 10 to the power 9 into Z2 minus Z1. We know it is 17.1. The total height is 17.1 centimeter. Into R, we will take as 82.06 since it is in CGS unit into 273 upon, we know the pressure given, this is 755 upon 760 since we need it in ATM into 2.303 log 755 upon 722. So we will obtain the value of DAB as 0.0636 centimeter square per second. This method of determining gas phase diffusivity suffers from several defects, like the cooling of the liquid by evaporation, the concentration of non-volatile impurities at the interface, and the climbing of liquid up the walls of the tube, and the curvature of meniscus. But we have assumed that all those problems are negligible here, and hence obtained our answer.